Hello, welcome to the Unit 13 test on redox. The title of each of these slides is going to include the name of another lesson that I have done on this channel. So if you find that you have difficulty with these questions, I recommend going back to that particular video. All right, let's get started. First up, what is the definition of reduction and oxidation? Very simply, reduction is gaining electrons and oxidation is losing those electrons. How do you know if a species has been reduced or oxidized? If the species has been reduced, obviously it has gained electrons, but in doing that, that means the oxidation state has dropped. It's important to remember that electrons are negative, so if extra electrons are taken on, the charge or the oxidation state is going to drop, becomes more negative. Alternatively, when something is oxidized, that means that it has lost electrons, losing negatives. In that case, the oxidation state is going to go up. Up next, what is the oxidation state of carbon in sodium oxalate? In order to solve these problems, I like to do what I call a QCT chart. Q stands for quantity, C stands for charge, and T stands for total. I know that because this is a compound, that the total of all of the oxidation states added together must equal 0. Using the periodic table for my two sodiums, I know that they are each +1 because sodium can only ever be +1. That is unless it's 0. So the sodiums in total will give me a charge of +2. Carbon is a little bit weird because it's a nonmetal that doesn't have a specific rule. So I just leave that as a question mark, but I do know that there's 2 carbons. And then with oxygen, oxygen has a rule that it is always -2. I have 4 of them, so all 4, each with a charge of -2, is going to give me an overall of -8. Doing the tiniest bit of algebra, +2 plus the mystery number -8 has to equal 0, meaning that the mystery number must be +6. That means that all of my carbons together carry a charge of +6, but because there's 2 of them, they each have a charge of +3. Write the oxidation and reduction half reactions for the following redox reaction. In my video on half reactions, I did mention that if you have a polyatomic ion that does not break down over time or over the course of the reaction, like this nitrate here, you can just keep the charge of the entire nitrate. You don't have to break it down into the nitrogen and oxygen, which is fantastic because nitrate is very easily -1. The zinc and the lead on their own as atoms or as elements have a charge of 0. And then when they are ions, you can use the reverse, the uncrisscross method to figure out their charge. For each of them, it is +2 when they are bonded to the nitrates. So after first figuring out the oxidation states of everything involved in this chemical reaction, it's pretty easy to find what changes. The zinc goes from 0 to +2, and the lead goes from +2 to 0. So looking at these reactions, zinc's charge is going up because it is losing electrons. So that would mean that the zinc is being oxidized. So there we have the oxidation half reaction. The lead starts out as +2 and becomes lead 0, lead the atom, and it does that by gaining electrons. So in this case, the lead is being reduced. Reduction is happening with lead when it is gaining those 2 electrons. A lot of tasks on this voltaic cell. It is a copper lithium voltaic cell, kind of typical of your average rechargeable battery these days. And the question asks you to determine the anode and cathode, write the half reactions, and make a statement on the changing mass of each electrode. I figured this one out using the activity series. Lithium is at the tippy top, and copper is not dead last, but it is pretty far down on the activity series, meaning that lithium is a really good anode. It loves to lose electrons. Because it is losing electrons, that means that it is undergoing oxidation. The lithium atoms are going to become lithium ions, giving away 2 electrons. Now, in this case, copper may have been +1, but more than likely the copper was going to be +2. Just kind of happens that way. Probably should have written that in the question, but either way, I wanted you to use the activity series for this one. So the copper is going to have copper ions, which are going to swim through the solution, go stick to that copper electrode, and in doing so, collect electrons traveling on that wire. When that happens, they are undergoing reduction because they are gaining electrons, and that is going to make copper the cathode. Cathodes increase their mass over time. Remember, the red cat gets fat. Reduction occurs at the cathode where mass is increasing, and lithium being the anode, the mass will decrease on that end of the battery. Another way to use the activity series is in single replacement reactions. So use the activity series to determine the products of these single replacement reactions. In the case of sodium and potassium chloride, there is no reaction. And the reason for that is because the potassium is higher up in the activity series than sodium is. Potassium is a much tougher metal. It is way more willing to lose electrons. So when that sodium approaches and says, hey, potassium, can I take that chlorine? Chlorine says, get lost. I'm giving my electrons to chlorine. You cannot have any part of this. So truthfully, no reaction will happen there. But in the copper and silver nitrate, the silver is a lot weaker than the copper. The copper is higher up in the activity series, so once it approaches that silver, it tells the silver, get lost, this nitrate belongs to me now, and the silver is going to be pushed out to be single, and the copper is able to take the nitrate. A bit more practice with the activity series. For each pairing, determine which would be the anode and which would be the cathode in the voltaic cell. Lithium and copper, we already did. Lithium is definitely higher in the activity series, so that would make that the anode. In iron and copper, iron is higher up, making iron the anode. Between lead and iron, iron is higher than lead, so iron will be the anode. And finally, in tin and potassium pairings, potassium will be the anode because it's a group 1 metal. It's definitely more active than tin. Last up are questions on the electrolytic cell. This one asks to determine the anode and cathode in this electrolytic cell. This one was a little tricky because there was nothing labeled here, but it is pretty easy to see that the anode is going to be on the left side of this particular image because the anode has to be attached to the positive end of the battery in order to pull the electrons out of the anode. The negative end is going to be attached to the cathode because the negative end of the battery is going to push the electrons into the cathode because they're negative. All right, that is everything on this redox test or study guide. If you did well, let me know. If you didn't do so well, let me know. What should I do another video on? Re-explaining with some examples, maybe. Leave any questions you have in the comment section below the video. Remember to go back to those titles to figure out if you need to rewatch any videos, anything that was a little tough. Make sure to head back to those videos. Subscribe so you don't miss the next unit. I'll see you there. Bye.